Uh, are you able to see my PPT screen and cursor?
Yes, sir.
Yes, sir.
Okay, this is what we were discussing in last class, Newton's law of viscosity. So just within say short time, I will explain what. So this was the situation before start of experiment. A lower plate, upper plate, everywhere, and it is filled with a fluid with a viscosity, some mu. Mu is the viscosity of the fluid in between these two plates. At time t less than 0, before start of experiment, this is the situation. Everywhere velocity is 0, and suddenly at time t equals to 0 and greater than equals to 0, so lower plate is given a force F such that velocity attained by lower plate is v. Continuous velocity v is attained by lower plate. Because of that, this first layer will attain a velocity v, and so on. As it will, this momentum will pass on to next molecule, next molecule, next molecule, and this plate is kept steady. So here you will get a velocity equals to 0. So under this situation, Newton's observed that this force applied on this plate, force per unit area, shear force, okay, shear stress, okay, shear force or shear stress applied on this plate is proportional to velocity gradient. So velocity per unit distance, velocity gradient is velocity per unit distance, and this proportionality constant is mu, and differential form of this equation is written tau yx, so equals to minus mu dvx by dy. So all the time we'll try to keep this flux positive, okay, because it is very difficult to have physical interpretation of negative flux. So we'll try to have this flux positive all the time. Hence this negative sign is coming into picture as velocity is decreasing with increasing y. That already we have discussed, and these two suffixes are very, very important. Tau yx. So x indicates direction of momentum, and y indicates in which direction this momentum is. There is a flux of momentum. So momentum is there in x direction, but we are discussing a molecular momentum flux in y direction, tau yx. Okay, so this is shear stress, rate of strain, rate of deformation or shear rate, and proportionality constant is called as viscosity. This is Newton's law of viscosity. So now if we look at this generalized, now till now you are aware about scalar and vector. Scalar is a physical quantity which doesn't have any direction. So vector is a physical quantity which will have one direction, like velocity here, Vx, Vy, Vz. So it has a direction associated with this velocity. So that is a vector. That is a vector. And now this is the physical quantity which will be associated with two direction. This is called as a tensor. Tensor, tensor. Okay, this is first time you might be hearing of this tensor. So this is the second order tensor. This is called as a second order tensor. Similarly, if you logically extrapolate, you can get a third order tensor. In mathematics, you can get fourth order tensor, sixth order tensor, and so on. So zeroth order tensor is nothing but vector, scalar. First order tensor is a vector. Second order tensor is called as a tensor, and thereafter we will designate that tensor with the order also. Say if you are a third order tensor, so you need to inform that, or you need to nomenclate accordingly. Third order tensor if some physical quantity is associated with a three direction. This is just a nomenclature, so we'll be using this definition towards the end of this subject, tensor. Okay, so this shear stress is nothing but the second order tensor, because two directions are associated with, and hence it is called as a tensor. Now if we generalize this equation, just forget about this is we are discussing about momentum transfer. So this is nothing but the flux. This is the flux, and mu is a transport property, and this is the gradient. This is the gradient of driving force. Okay, here the gradient of make sure your mic is off all the time. Okay, so if you want to ask some question, then only you switch on your mic. Okay, so this is the flux. Okay, flux transport property into gradient. Now we are discussing momentum transfer. So certainly this is the momentum flux. Okay. Now whether shear stress is a momentum flux, shear stress can be named as a momentum flux or not. So roll number 11 for Yuvraj.
Yes, sir.
What is the unit of momentum?
Sir, sir,
Momentum. Unit of momentum. What is momentum?
sir, momentum is just like mass of body, mass of a body.
Mass multiplied by
So mass multiplied by velocity.
mass multiplied by velocity. So mass multiplied by velocity, and what will be momentum flux?
So, uh, so, so like material of the body moving.
Momentum flux. Momentum flux. What is the definition of flux? Yeah, roll number 68. Me too.
Yes, sir.
Yeah. So what is momentum flux?
You're like the flow of a substance through unit area.
Okay. So what will be momentum flux?
Sir, means unit of sir
Momentum
like
flux.
rate of transfer of movement across a unit area.
Yeah, yeah. So it will be momentum per unit time per unit area.
Yes, yes.
Okay. And what is momentum? Everybody please note down. Okay, you write a notes actually. You can write the important notes whenever we are discussing. So it will be momentum per unit area per unit time. Okay. So this will be nothing but a force per unit area. Force per unit area. This will be equals to force per unit area. Momentum, okay, per unit time is nothing but force. So momentum is mass into velocity, and velocity per unit time is a acceleration. Mass into acceleration is a force. So momentum per unit time per unit area is nothing but the force per unit area. Everybody got this? Anybody has any difficulty? Momentum per unit time per unit area. Okay, momentum per unit time per unit area. This is the momentum per unit time per unit area or shear stress. Okay, this is called as a flux. We are calling it as a flux. We are calling it as a momentum flux. We just try to confirm. We are just trying to confirm momentum flux is nothing but the force per unit area or shear stress. Shear stress is nothing but the momentum per unit area. So this is shear stress. Shear stress is a force per unit area, and force is a mass into acceleration. Mass into acceleration is nothing but mass into velocity per unit time, and mass into velocity per unit time per unit area is nothing but the momentum flux. Everybody got this? Yeah, roll number 49, Harshavardhan.
Yes, sir.
Yeah, can you just explain what I told you just now? Shear stress can be interpreted as a momentum flux. How?
Momentum flux, the units will be Newton per meter square.
Very
And
good.
shear stress also, if you were to look at its unit, it will be force upon area. So even
Uh-huh.
that becomes Newton per meter square. So we can say that shear stress
Can you just explain the steps in between? how
Yes, sir.
this shear stress force per unit area can be interpreted as a momentum flux. Flux is nothing but a quantity per unit time per unit area. So momentum flux is a momentum per unit time per unit area. Just explain the intermediate steps.
Yes, sir. So momentum flux will be the unit of momentum is kilogram meter per second
Very good.
upon second into area, which is meter square.
Uh-huh.
So Newton is kilogram meter per second square. So we get that
Okay,
upon
okay.
area, which is meter square.
Yeah. So as you are discussing everything with respect to unit only, so fundamentally also with respect to physical property also you can explain. Like shear stress is a force per unit area, and force is nothing but mass into acceleration. Mass into acceleration can be written like mass into velocity per unit time. Velocity per unit time is a acceleration. Now mass into velocity is a momentum. Momentum per unit area per unit time. Momentum per unit area per unit time is nothing but the flux. Okay, so everybody got this. Now till now you was referring this quantity as a shear stress, tau Ix as a shear stress, but hereafter we will referring same quantity shear stress as a momentum flux. That is why I am giving you a here actually. Why I am, because it is not the different. Okay, in transport phenomena we will call it as a momentum flux. If you go to fluid mechanics or applied mechanics or some other mechanics subjects, then same quantity is called as a shear stress. So shear stress can be interpreted as a momentum flux. This is very, very important. Otherwise, you will miss. You will think that momentum flux is altogether different. It is not at all different. It is same quantity. Only we are renaming the quantity. We are renaming the quantity, or we are addressing same quantity with a different name. Initially, till now, you were referring this quantity as a shear stress. Now, same shear stress is referred as a momentum flux. Anybody has any doubt in this? Very important, because hereafter I will never refer shear stress. I will always refer momentum flux. I will always refer momentum flux, but it doesn't mean that you are studying this first time. This you have studied so many times shear stress. So same fundamental is for momentum flux also. Okay. So this is a momentum flux into transport property into velocity gradient. So this will be the equation for you can say fluid mechanics. Fluid mechanics momentum flux multiplied by, that will be equals to transport property multiplied by velocity gradient. This negative or positive sign depends upon what will the direction of this gradient. If this gradient is negative, then we'll put this sign negative. If this gradient is positive, then we'll put this sign as a positive, so that all the time our momentum flux will be positive. Because this flux, whenever I am referring to flux, so negative value of flux, it is very difficult to justify the physical significance of negative value of flux. Okay, negative value of flux. So it is all corresponding to your you can say origin, where you are taking it as an origin. It can be negative or positive, but all the time, so we will not associate that direction with flux. It will be always flux. Okay, flux will keep. This is just for a comparison purpose. Okay, so this is for comparison purpose. This momentum flux will be always positive. Accordingly, I will be getting this negative sign or positive sign. If velocity gradient is negative, as in this case, this velocity gradient is negative. So I'm getting this as a negative sign here. So this is the Newton's law of viscosity. Now we'll just go in this consistency of units and all. Okay, whether it is consistent with units and all, because this is very, very important whenever you are solving some problem on this Newton's law of viscosity. And there are a couple of problem asked in GATE also, that is just based on a unit consistency itself. Okay, because if you go to second law of Newton's law of viscosity, or for Newton's law of viscosity for non-Newtonian fluid, a similar law, power law, it is called as a power law for non-Newtonian fluid and all. That time you should able to correlate what is the viscosity there and what is the viscosity in Newton's law of viscosity. So this here for that this unit consistency is very very important, and this is the direction of momentum flux. What is the direction of momentum flux? I have x momentum. Momentum is there in x direction. Okay, momentum is there in x direction, but it is flowing in y direction. This is transport of momentum. We are discussing using Newton's law of viscosity is x momentum. How x momentum flowing in y direction. So this suffix is very very important. So first suffix indicates how this what is the direction of momentum flux, and second suffix indicates what is the direction of momentum. So this indicates a momentum direction, and this indicates a momentum flux direction. So this you should remember always. Okay, as I am telling that. Okay, even though this looks very simple, and you might have studied this so many times in past also, this flux, Newton's law of viscosity. But as we are comparing, so you should not forget these basic terminologies which we are using actually, like flux, then what is momentum flux, what is the transport property in heat transfer, what is transport property in momentum transfer, what is transfer, and what is the gradient and all. So this is very very important. So tau yx is also called as a x momentum in y direction. What is the how to in statement wise it is called as a flux of x momentum in y direction. This is what I was referring every time. So this unit of viscosity is poise and centipoise. So poise and centipoise, which is a CGS unit and which is the MKS unit? Yeah, roll number 53. Roll number
Hello.
53, Shivam.
Yes, sir. Hello.
So poise and centipoise.
Yes, sir.
Viscosity has generally referred into two units, poise and centipoise. So which is the
Yes.
CGS unit of viscosity?
So CGS unit is poise.
Very good, excellent. So this is what generally people will make a mistake. Okay, because centipoise and CGS unit generally or most of the CGS unit will start with centi or cm and so on. So people will make a mistake, and there itself, and this kind of questions will be asked in GATE exam. Very simple, but you need to keep the presence of mind actually. So this is the SI unit. Okay, this is the SI unit. SI unit. This will be Newton per meter square. Okay, Newton per meter square, meter per second, and meter. Okay, this is Pascal second. Okay, this is Pascal second. This is the viscosity, unit of viscosity. So this is Newton per meter square. This is unit of viscosity. This is Newton per meter square, and this velocity is meter per second divided by meter per second divided by meter. So this is what the unit of velocity gradient. This is the velocity gradient, and this is the unit of momentum flux. And the Newton per meter square is a Pascal. Newton per meter square is a Pascal, and a second per second is second. So Pascal second is a unit of viscosity. Pascal second. This is nothing but Newton per meter square second. If you rearrange this equation, so Newton is again force is mass into acceleration. So kg meters per second square into second. So this is also unit of viscosity, kg per meter second. So Pascal second will be equals to Newton per meter square second or equals to kg per meter square per second. So this second sometime will be in a numerator, sometime will be in denominator. So both are correct. So kg per meter per second. This is also unit of viscosity. Newton per meter square into second. That is also unit of viscosity. Both is equals to Pascal second. And this is the SI unit of system. Okay, SI unit of system. And this is poise is nothing but a gram per centimeter second. So poise is name of the scientist. So he has defined this. So why they have taken this equals to poise and this equals to Newton's? It is nothing to do with the physics of the problem. Okay, because poise can be name of the one scientist, and he has used this unit first and defined this as a poise, and Newton has used this unit as a Newton. So that's all. So poise, so gram centimeter second. So this is not a MKS unit or SI unit of system. Poise is not in This is the CGS unit. So centipoise, 1 centipoise equals to 100 poise. None. It is reverse. So 1 poise equals to 100 centipoise. So 1 centipoise equals to 1 upon 100 poise. So 1 upon 100 poise. So 1 Pascal second will be equals to 10 poise. So SI unit. So SI unit 1 Pascal second equals to 10 poise, and that will be equals to 10 raised to 3 centipoise. So these units are discussed here just to keep you in mind actually this importance of units. And there is a confusion, little confusion in describing the name of these viscosity units, name of the viscosity unit. And generally in competitive exam like GATE, they will be targeting this kind of questions only where there is some confusion or something is there. So that's why this unit of viscosity is very, very important to know and understand and keep in mind all the time. So this is what unit of viscosity is there. So anybody, any confusion over this Newton's law of viscosity? Okay. Then now we'll move on to Fourier law of heat conduction. This is just a problem. So we'll try to solve this problem in say maybe in tutorials or so. So and then tutorial is kept just for solving the problem. So just leave aside that problem. So we'll move on to Fourier law of heat conduction. So Fourier law of heat conduction, and Pratesh is there in class.
Yes, sir.
Yeah, so I told you to give me one slot of 2 hours for these tutorials.
Yes, sir.
So when it is possible?
Sir, exactly 2 hours is not like you can have 1 hour with 1 hour class. Like that is very much possible.
1 hour actually you can have, you can adjust with other practical batches and give me whole class 2 hours. Okay,
But that's
just
what
think over this. Think over this, because problem solving, initially I need to repeat all the fundamentals of that problem, explain the problem, solve the problem, and it will be very slow. So generally, this tutorial slots will be of 2 hours.
actually what happens in the evening slot. In evening we do not have any this regular class slot.
Uh-huh.
It is all lab and TNP activities going on in that part.
Yeah. So you just
But currently,
give the time to all the labs and everything, and keep 2 hours slot for transport phenomena, and just let me know which slot is suitable for all of you. Okay. You just think over and
yes,
let
sir.
me know. Okay. So now
Yes,
we'll
sir. Yes,
discuss
sir.
Fourier law of heat conduction. So Fourier law of heat conduction. So already you have discussed Fourier law of heat conduction in heat transfer. Now what is the difference? So this case which we defined in Newton's law of viscosity, we'll try to define identical case in heat transfer now. Identical case in heat transfer, and main purpose of discussing Fourier law of heat conduction here is just to you can say compare Newton's law of viscosity and Fourier law of heat conduction, and just to make ourselves convince ourselves that these two laws are similar to each other. Only the difference is that is the law for momentum transfer, and this is the law for heat transfer. This is the only difference. Otherwise, these both laws are similar. To convince ourselves, this is the first time you are now trying to correlate heat transfer with momentum transfer. So certainly it is not very easy to digest that Newton's law of viscosity is same as the Fourier law of heat conduction. So hence that case and all properties and everything is defined in such a way that, so this is the first time you will be trying to convince yourself that something is similar in heat transfer as that of Newton's law of viscosity in momentum transfer. That is our main aim. So this is what you can say identical figure is defined. Okay, identical figure is defined. So what is this figure? Is that there is some solid material is there. This is say material A, and this is also material A. So some material is there which is heated, which is kept at constant temperature. So this is heated or cooled, that doesn't mean, it is kept at constant temperature, and there is some solid material in between. Here also some solid material is there. There it was a fluid. So here it is a solid material, and this from between this distance y. So there is a solid material of which thermal conductivity is K. Okay, of which thermal conductivity is K, and at before start of experiment, whole of the system is kept at temperature T0. So this material is at T0, this sandwich material is at T0, and this upper material is also at T0. Okay, so at time T equals to 0, suddenly the temperature of bottom plate is increased. Okay, temperature of bottom plate is increased to temperature T1. Now no slip boundary condition here also tells that as at the interface the temperature will be same. So certainly the first layer of this sandwich material will be having a temperature T1 as at time T equals to 0, and slowly this plate is kept at constant temperature T0. Okay, certainly if energy is given to this plate to maintain the temperature T1, certainly that energy should be removed from this plate so that this temperature is kept at T0 constant throughout. So this will not increase over T0. This will be kept at constant. So whatever energy coming in this direction should be removed. Equal amount of energy is removed. Then only I can keep this temperature constant at T0. Now because of this conduction, this sandwich material is also solid. Because of this conduction, the heat will be transported in y direction. This T1 is greater than T0. T1 is greater than T0, and heat is transported in y direction, and there will be some temperature profile set in this sandwich material. So we are discussing this sandwich material only. This upper plate and bottom plate is given just to provide the heat and to remove the heat. Our system, okay, material of concern is this sandwich material. So there is a heat transport from in y direction. There is a heat transport in y direction because there is a temperature gradient. This temp T1 is greater than T0, hence temperature will be transported, and slowly some temperature profile will set. So this will be the direction of energy flux. As initially also I told that it is very easy to understand direction of energy flux. Okay, because conduction very easy to understand. Okay, here I have solid material. If this is kept at temperature T1 and this is kept at temperature T0 and T1 is greater than T0, so it is very easy to visualize that energy or heat will be flowing in this direction. Same was the case in momentum transfer, but that time it was very difficult to visualize how this momentum is transported in y direction. When fluid is moving in x direction, how this momentum was transported in y direction. But it is very easy. Okay, so this will be direction of energy flux. So this will be the kind of temperature profile set. Now you can see figures are exactly identical. At time t equals to 0, this lower plate is given temperature T1. So here temperature is T1 everywhere. At this layer temperature is T1 everywhere. In all other layer the temperature is 0, T0. Temperature is T0 everywhere else. Okay, temperature is T0 everywhere else. Only at y equals to 0 temperature is T1. Okay, only at y equals to 0. So this is the temperature profile. This x-axis and y-axis is the temperature profile at t equals to 0. Okay, at t equals to 0, this x-axis, this y-axis and x-axis is the temperature profile, which is giving me temperature with respect to coordinates. Temperature profile is nothing but the equation or some information which will give me a temperature variation with location. So at time t equals to 0, this is t. This t stands for time. Small t stands for time, and capital T stands for temperature. This is standard nomenclature. Until and unless it is mentioned, you take it as this capital T as a temperature and small t as a time. So at time t equals to 0, so temperature everywhere else is T0, only at this surface. At y equals to 0, temperature is T1. So this is the temperature profile at time t equals to 0. Slowly, this energy will be transported in this direction. Slowly, this energy will be transported and temperature will increase. Temperature will increase. Say temperature is increased up to this point. Up to this point. So from this plate, upper plate, till this point. So till this point, the temperature is T0 still, and thereafter it will slowly increase to temperature T1. So this will be the temperature profile. This will be the temperature profile at time t equals to T1. This is time t equals to T1. So this will be the temperature profile. This straight line coming up to this point, and thereafter temperature is increasing. Temperature, and this is temperature axis. This is the distance. So slowly it will increase and it will go to temperature T1, and this is T2. This is some greater time than T1. This is some greater time than T1. So now this energy is moving in this direction. It is penetrated till this point. Till this point it is penetrated. So here still temperature is T1. Here in this region still temperature is T1, and thereafter slowly it is increased and temperature is reaching to T1. So here temperature is T0. Here temperature is T0, and slowly it is increasing and reaching to T1. So this is the temperature profile. It will start at, say, y equals to capital Y. So reducing the value of y, coming down till this point. Till this point temperature is T0, and thereafter it will be slowly increase, and it will reaching to temperature T1. This is time T1, and these all are a transient temperature profile. Transient temperature profile. So Fourier law is not for transient temperature profile. It is for steady state temperature profile. At steady state, when I wait for, say, longer time, and keeping this temperature constant at T0, this is forcefully I need to keep. Forcefully I need to remove the energy from this plate. That energy will be equals to the energy supplied at this plate after steady state. Once steady state is achieved, so some energy will be removed, so that upper plate is kept at temperature T0. So this will be the temperature profile. At steady state. So this is the temperature profile at steady state, and we are interested in this steady state temperature profile only. We will not go in details of this transient temperature profile. So because it is very, as I told, it needs a partial. Your partial variation will be with respect to distance, partial variation with respect to time. So both are playing a role here. So certainly partial differential equations are involved. So this discussing this transient temperature profile will be very complicated mathematically. So currently we are not looking into this transient temperature profile. In this transport phenomena subject also will not look into transient zone. We'll look into steady state temperature profile only, always. So generally we'll start the subject with simplicity. So if you are very much interested, maybe if you, when you go for MTech and all, that time you will have this advanced transport phenomena, that is altogether dealing with the transient velocity profile, transient temperature profile, transient concentration. Everywhere partial differential equation will be there, but this fundamental transport phenomena will be dealing with the steady state temperature profile only. So what is the steady state temperature profile is, and this is the observation made by Fourier. So rate of heat transfer per unit area is proportional to temperature gradient. So this is the observation made by Fourier. So at steady state, if I am keeping this upper plate at constant T0 and lower plate at constant T1, so rate of heat transfer per unit area. So I can estimate the rate of heat transfer per unit area. What will be the flux? This is rate of heat transfer. So this is again standard nomenclature, Q dot. So this is Q dot is a standard nomenclature for rate. Q, capital Q is a rate, dot. Q dot is the rate of heat transfer per unit area. So heat flux in this direction, okay, in this direction is directly proportional to a temperature gradient. This is not temperature difference. This is temperature gradient. Means difference of temperature per unit length. Okay, that is temperature gradient. And this proportionality constant, okay, proportionality constant is nothing but the thermal conductivity. Proportionality constant is thermal conductivity. So here you can see this is positive sign. Okay, here you can see this is positive sign, whether it should be positive. So here del T is positive, yeah. So because temperature is reducing, okay, temperature is also reducing. No, it should be negative. Here also it should be negative sign actually. So it is given. So T1 minus T0. T1 minus T0 is given. So it is, they are considering this as a negative, okay? Negative gradient. This is negative gradient. So T1 minus T0. Okay, this is positive quantity, hence this positive is there. So this is proportionality constant is thermal conductivity. Proportionality K is a thermal conductivity constant. Okay, K is a thermal conductivity, which is a constant, and differential form of this equation is Qy equals to minus K dt by dy. Again, this gradient is negative. Here gradient is defined in opposite direction, hence this was positive. This gradient is negative because my origin is here. Y is increasing, temperature is decreasing, so this will be negative. So minus K dt by dy. So certainly this will be a heat flux equals to thermal conductivity into temperature difference. Okay, heat flux. Now here you can see flux. Okay, heat flux. Transport property is thermal conductivity, and this gradient is gradient of temperature. Okay, this is the Fourier law of heat conduction. This is Fourier law of heat conduction. So this is clear to everybody. Anybody
Yes,
has any
sir.
doubt? Yeah, any? Oh, very good, very good. So 29 Vedant, roll number 29 Vedant.
Yes, sir.
So velocity in momentum transfer.
Yes, sir.
Just listen to me carefully. Velocity in momentum transfer is similar to which property in heat transfer?
So sir, looking from the formula, we have the velocity gradient and here we have temperature gradient. So where there is in momentum transfer, we have velocity. So here we will have temperature.
Excellent, excellent. So, so this is like comparing two families. Okay, comparing two families. So we cannot tell it as the same. It is similar. Okay,
Yes, sir.
these are similar. Temperature has some role to play in heat transfer area. So this family is heat transfer. So temperature has some role to play in heat transfer. Same role is played by velocity in momentum transfer. This is clear to everybody.
Yes, sir.
Roll number 25, Nivas.
Sir.
So the thermal conductivity in heat transfer, okay, thermal conductivity in heat transfer is similar to which property in momentum transfer?
Mu transfer property.
Yeah, thermal conductivity in heat transfer is similar to which property in momentum transfer?
Transfer property.
Are transport property? What is the name of the transport property in momentum transfer?
This mu did not.
What is the name of that property? Roll number 1, Abhinav.
So viscosity.
Viscosity, very good. Roll number 1, Abhinav, why there is negative sign here in Fourier law of heat conduction also and Fick's law of diffusion also? Negative.
Yes, sir. Sir, the flux is a positive quantity, and the gradient, the temperature gradient and the velocity gradient is negative because with increase in y, there is decrease in temperature here and velocity in Newton's law of viscosity. So that's why.
Okay. So what is the energy similar to which quantity? Here energy, if I call heat in heat transfer, what will be the quantity in fluid mechanics?
So shear stress,
Shear stress, or it is
uh,
called as a,
mo momentum flux.
not, I am calling it a heat, energy.
Uh,
Energy. Heat is
mom
similar to which quantity in
momentum,
momentum transfer?
momentum, sir.
Momentum. That is what I was telling, that if you understood this, okay, that heat transfer is similar to a momentum transfer. So if you are expert in energy transport, energy flux you are expert in, so logically you can have some interpretation of some behavior in momentum transfer also. Fluid mechanics also you can study. Same is the case if you are expert in fluid mechanics. So certainly logically you can extrapolate that information for heat transfer also. Okay. So this is what. So we'll solve the problem first. Okay. Just to improve the understanding, take down the information from this problem. A Newtonian fluid with a viscosity 10 centipoise is placed between two large parallel plates. So here I have one plate. Okay. So here one plate is there. Here one plate is there. So Newtonian fluid is kept in between. Okay. Newtonian fluid means the fluid which will follow Newton's law of viscosity. So between large areas, viscosity is 10 centipoise. 10 centipoise, viscosity is 10 centipoise placed between two parallel plates. The distance between these two parallel plates is 4 mm. So distance is this y equals to 4 mm. The rover plate is pulled in positive x direction. This is pulled in positive x direction. Force is 0.5 Newton. So force is 0.5 Newton, and which is giving the velocity v1 equals to 0.1 meter per second. Okay, 0.1 meter per second. This is vx. Vx will be equals to 0.1 meters per second. Fx equals to, so F equals to 0.5 Newton, and that is in positive x direction. So while the upper plate is pulled in negative x direction with a force 2 Newton, upper plate is pulled negative. So so 2 Newton. Each plate has an area. This plate has an area x multiplied by z. This will be the area. This x multiplied by z. This will be the area. Area equals to 2.5 Newton meter square. 2.5 meter square. If the velocity of lower plate is 0.1 meter per second, calculate the steady momentum flux. So what will be the shear force on the plate? What will be shear force on the plate? Roll number 6. Aksh.
So the total shear force, it would be of 2.5 Newton.
Very good, excellent. So that fundamentals you got it from, say, applied mechanics or fluid mechanics. Even though these are negative minus 2 Newton, this is plus 0.5 Newton, but we are discussing shear force. Shear force will be a addition of this opposite direction. In fact, here also this will be 0.5 Newton per meter square. So shear force will be 0. If this is also given a force 0.5 Newton per meter square, this is also given a 0.5 Newton per meter square in x direction only. Shear force will be 0. Shear force is 2.5 Newton. And now what is steady state momentum flux? Momentum flux is nothing but the shear stress. Okay, this is shear force. Shear force is 0.5 plus 2.5 Newton, and shear stress is nothing but the momentum flux. So what will be the momentum flux? Aksh?
So 1. So 1
1.
will, it will be
Okay, it will
divided
be
by
a,
area.
shear force divided by area, 1 Newton per meter square. Okay.
Yes.
So this is the shear stress. Okay, shear stress in this area. Okay, in this area, shear stress will be a momentum flux. Momentum flux in this area will be a 1 Newton per meter square. Now, if say velocity of bottom plate is 0.1 meter per second, what will be velocity of top plate if viscosity is 10 centipoise? First of all, convert this 10 centipoise into a SI unit. Okay, 10 centipoise. So 1 centipoise will be equals to here. Here it is given. Here 1 centipoise will be equals to 1 centipoise equals to 10 raised to minus 3 Pascal second. Okay, 1 centipoise equals to 10 raised to minus 3 Pascal second. So 10 centipoise will be equals to 10 raised to minus 2. 10 raised to minus 2 Pascal second. And this gradient of velocity, okay, gradient of velocity that you can calculate because this distance is given and this velocity is given. So once you get the gradient using this equation, you substitute this and get the velocity of this upper plate. Get the velocity of upper plate. Roll number 31. Roll number 31. Roll number 31. Roll number 64, Shubham.
Yes, sir.
Yeah. What will be the
6.
gradient, velocity gradient, first of all?
Velocity, so directly I can tell velocity. I have
So you can
calculated.
get a velocity gradient from this equation itself because you have momentum
Yeah.
flux. Momentum flux will be equals to viscosity into velocity gradient. So what will be
Hmm.
velocity gradient?
Uh, 0, 0.6.
Okay. And then what will be the velocity of upper plate?
0.06 meter per second.
0.0606.
Yes, sir.
Yeah, anybody else has any other answer?
Sir, velocity gradient dv by dy will be minus 100.
Minus 100. And what
and
will be the velocity of upper plate?
sir,
And
sir,
this is
if we
mm. This distance is in mm.
yes, sir, we have to convert it into meters.
Yeah, yeah.
So, if we consider velocity of the upper plate at v2, then v2 minus 0.1 is equal to uh, uh,
Divided by this distance. That is equals
yes,
to velocity
divided by
gradient.
4 into 10 to the power minus 3 is equal to minus 100.
Okay.
So from
It
that
is
we
0.3
get
meters in negative x
yes, sir.
direction.
0.3
It will
meter per second in negative x
Negative x
direction.
negative x direction.
Yeah, 0.3 na?
Yes, sir.
So anybody else is getting this answer? So you can write in chat box.
Yes, sir.
So everybody is getting this thing.
Hello, sir.
Yeah, tell me.
Can you explain? Can you please explain again? I not got this concept.
Okay, you got momentum flux. You got momentum flux.
Yes, sir. Momentum flux 1.
So now Newton's law of viscosity tells that momentum flux equals to viscosity into velocity gradient. And viscosity is 10 centipoise. Viscosity is 10 centipoise. So you can get the velocity gradient. And velocity gradient is velocity gradient means what? dv by dy. So I have
Yes,
v1 and this will be v2. v2 minus v1 divided by y2 minus y1. This is velocity gradient. So you can get the v2. Is it okay?
Now got, sir. Now got.
So
Yes, sir.
here you can
Thank you,
see.
sir.
Here you can see.
Now got, sir.
So This is 1 Pascal second. Okay, this you got? This you got?
Yes, sir. This what, sir? Shear
Okay,
momentum flux shear
and
force.
this actually this tau yx divided by mu is nothing but your velocity gradient. Tau yx divided by mu is nothing but your velocity gradient. This is v2 minus v1 divided by y2 minus y1, and y1 is equals to 0. Y1 equals to 0, hence it is not used. So rearranging this Newton's law of viscosity, this velocity will be minus 0.3. Minus 0.3 minus sign indicates the velocity is in negative. So you can see this dvx by dy is minus 100 second inverse. This will be the velocity gradient.
Sir, I have one doubt, sir. How
Yeah,
we
tell
got
me.
my 0.1 is here V2 is equal to 0.1
So it is
minus how
given.
we got 0.1?
It is given here.
Oh, okay, sir. Okay, sir.
Can't you
Got, sir.
see
Thank
here
you,
also
sir.
it is given?
Got, sir. Got, sir.
Okay, here also it is given that okay, this v1 is
Okay,
given
sir. Got,
equals
sir.
to 0.1 meter per second. So you can see complete slide na, there is no cut of the slide. Pritesh, Faguni, are you able to hear me? Somebody else.
Yes, sir. Yes, sir. Sir,
Yes,
my
sir.
mic
Yes,
is
sir.
We
muted.
can
I
see.
couldn't hear you.
So you can see this v1 na?
Yes, sir.
Yes, sir.
Yes, sir.
You can see my cursor. Now
Yes, sir.
also you can see my cursor. It is on A.
Yes, sir.
Okay, so complete slide is visible na? Okay.
Yes, sir.
So this is for momentum transfer. Same problem we can solve it for heat transfer also. Heat transfer is flux. Energy flux equals to transfer property into temperature gradient. So you can see one side of the copper slab receives the net heat input at the rate of 500 watt. 500 watt is energy per unit second, joule per second. Okay, 500 watt due to radiation, and other phase is hold at the temperature 35 degrees Celsius. Other phase is hold at a 35 degrees Celsius. If steady state condition prevails, calculate the surface temperature of the side receiving a energy, radiant energy. Surface phase area is 0.5 meter square, and thermal conductivity, thickness of the slab is 4 centimeter, and copper plate is 4. For copper plate, thermal conductivity is 398 watt per meter Kelvin. Just get me the answer. What will be the temperature of the upper plate, or what will be the temperature of the plate which is receiving the energy?
45 degrees Celsius, sir.
45 degrees Celsius. It is very easy to solve. Now, how many of you are able to solve the problem? Can you just let me know in chat box? How many of you are able to solve the problem? Yeah, very good, very good. This is what point to be noted. Point to be noted that molecular flux in heat transfer is very difficult, very easy to understand. So because without a single questions, everybody is able to solve the problem in heat transfer. This is why it is very easy to visualize the conduction in heat transfer. Very easy to visualize, and moreover more stress is given, more concentration or more time is given in heat transfer subject also studying a conductive heat transfer. That is also one point. You might have spent more than 10 classes on conductive heat transfer, but this doesn't mean that you are not studied Newton's law of viscosity, because both are similar. Same ideologically, you can study the Newton's law of viscosity also. So this is what the point to be noted that okay. So here you can see. So here I am getting the energy 500 watt. So 500 watt. So flux will be a 500 divided by 0.5. So watt per meter square. So it will be 10,000 something. and here temperature is 35 degrees Celsius. So what will be the temperature here? So you can calculate the temperature gradient. Thermal conductivity is given, so you can just rate of energy is given. So you can say 100,000 watt per meter square. This is the flux, and flux will be equal to, this is the Fourier law of heat conduction. This is 45.1 degrees Celsius. Okay, 45.1 degrees Celsius. Everybody got this? Anybody not getting this? Okay. Okay, so we'll stop this class, today's class here itself, and we'll continue in next class. Anybody has any doubt can stay back and clear your doubt. Otherwise, you can leave the class.